Okay, so hello everyone. I'm so excited to welcome you to our first TNT seminar. Our first speaker is going to be Dr. Marom Bikson. He's joining us here today from the City College of New York of the City University of New York, where he leads the CCNY Neural Engineering Group. He received his bachelor's degree from the biomedical department right here at Johns Hopkins and received his PhD from Case Western Reserve University. He was also a research fellow at the University of Birmingham Medical School in the UK before becoming a professor at CCNY. He's best known for his work on brain targeting with electrical stimulation. The translational R&D activity of his group spans preclinical studies, computational models, device design and fabrication, regulatory activities, and clinical trials. Dr. Bikson has also co-invented high-definition transcranial direct current stimulation, or HDTDCS, the first non-invasive targeted and low-intensity neuromodulation technology. In addition to his work in lab, he has spent time consulting biomedical companies such as Boston Scientific and government agencies, is actively involved in biomedical education, holding events including NYC Neuromodulation Conference and the Neuromodic TDCS workshop, and is co-founder and CEO of Soteric Medical Inc., which produces neuromodulation technologies for clinical trials and human performance testing based on findings from his research. We're excited to have him with us today to talk about one of, sorry guys.
Not necessarily what they said to do.
Yeah.
Can somebody mute? Sorry. We're excited to have him here with us today to talk about one of the major focuses of his research work, understanding interactions between direct current stimulation and neural circuits. Thank you for being here, Dr. Bikson.
Thanks. I really appreciate the invitation. It does feel a little bit like coming home, since this is where I sort of started my professional career. And so I hope you can hear my slides and let me know if there's any connectivity issues or anything like that. I wanted to give both a talk that's a bit technical and covers things that I'm really excited about right now,
You had a presentation,
but also maybe address some of these translational aspects that we're talking about as well. Okay. These are my disclosures. These are includes companies that I'm currently actively working with, but I think it's good to emphasize that, my group, like many others, really welcomes collaboration with industry, and it's an important outlet for our own work. And I'll be putting these slides in a little bit. I haven't done them yet on my Twitter account, as well as a link to all the papers I'll be discussing, because in some cases, I think I'll be touching on things at a pretty high level. There's a concept that I call translational neural engineering or translational medical device development, and I don't really think it's unique to our group. There's certain groups in Johns Hopkins, I think, that really exemplify this approach. But the idea with doing translational neural engineering is that you're focused on reducing human suffering. So that's really the output, and that is not necessarily a commercial goal. And it's not, it could be something, for example, where you help a single individual who is suffering, but it's really about reduction in suffering. And I think in our academic, ivory tower, it's sometimes easy to lose sight of that there's this direction where we want our work to be impactful. And the process begins with a scientific hypothesis, right? That scientific hypothesis could be something like, the ability to deliver DC current invasively to this brain region may alleviate pain, right? Or something like that. So there's a scientific hypothesis, but between the hypothesis and the new treatment are many steps. And these are the general kind of steps that we tend to think about. If there is a commercial aim, there's thoughts about intellectual property. There's the device design itself, like the classical component of what we think of. I know when I was coming in as an undergraduate, at JHU, that's what I wanted to do, device design. That's what most people want to do. But beyond the design, there's the manufacturing, being FDA compliant, which gets you into the more formal regulatory stages of approval. There's the preclinical testing. I used to call that animal models, things like that. But in this context of the spectrum, we would call it preclinical testing, and also different kinds of clinical trials as well. And I think, these tend to be often siloed. There are certainly specialties. There are people who spend their entire life on just one of these. But there's also the idea that maybe all of these constitute a continuum of device design, and that the most effective way to get from one point to the other point is by having if not expertise, at least familiarity with all these different steps. So this is this notion of design as a continuum. And I'm not going to be saying more about this, but I did want to, because of this translational theme here, I did want to mention it. I mean, there's certain examples that, I could bring up. For example, let's say you're a graduate student and you have the opportunity to test a new drug. And you have two options, right? One option is like a food grade chemical, right? That's already FDA cleared for children's candy. And the other one is some sort of very fancy nano something particle, which you don't even know if it's lethal or not. And from an academic perspective, clearly one of them has maybe a little bit more of an appeal, right? As far as this is going to get me more cachet, this is much more exciting. In principle, this molecule can be engineered to do this and that. And this is just like, the Twizzlers die, you know what I mean? But if you're thinking about it from a regulatory perspective already, you may realize that in that nanoparticle case, you're looking at 2 decades before first in man, right? Or 1 decade, but you're going to need $100 million. Well, with the food dye, that process would be extremely accelerated. So it's an example where on the preclinical, you might be thinking on the regulatory. And I think there's many other touch points like that as well. Should you pursue intellectual property? I've had projects where we've done that. I've also had projects where we specifically did not pursue intellectual property, and that led to opportunities for deployment. Again, depending on what the goal is. And so I think those are just some thoughts in the continuum. Now, we work on different kinds of devices, but a lot of our work is on neuromodulation and brain stimulation. This is very familiar to this audience, so I can just gloss over this aspect of it. Brain stimulation technologies have different names. The names usually are how the energy gets into the body. So deep brain stimulation, we're going to drill a hole in the skull and implant an electrode. Spinal cord stimulation, transcranial magnetic stimulation using induction. Electroconvulsive therapy is a technique actually where it's non-invasive, but so much electricity is put into the brain that a seizure is produced. And then that leads to secondary therapeutic outcomes. And then you have this final class of technologies, which are transcranial electrical stimulation, of which TDCS, which I'm going to talk a bit about, is one of them. And I like to kind of classify these as implant treatments, so things that you need surgery for, in-hospital treatments, things that you they're non-invasive, but this is not something that you could currently do at home. And then ultimately, what to use a catchy phrase, wearable. So things that are battery powered, they could be applied in the hospital, but theoretically, you could also have them shipped to your house. And that's certainly the trend of things. And I'll focus a bit on that, but I'll touch on some of the other ones, and specifically a technology that is near to dear to me, and also to some groups at here as well, right? Is using direct current stimulation as a therapeutic modality. Now, transcranial direct current stimulation is a bit of an oddball in one particular sense. Instead of using pulses, which are the universal case, and deep brain stimulation, spinal cord stimulation, transcranial magnetic stimulation, in this case, a direct current is applied. So like what you would get from a 9-volt battery, though this is current controlled. This is traditionally non-invasive because of the toxicity associated with it. There's really, I think, just one group, and it's by you, that's thinking about how to apply this invasively. But it's traditionally non-invasive technique with electrodes applied through electrodes on the head. And this is a very popular technique. I mean, by the time from when I start this talk to when I finish this talk, there'll be 1 or 2 more papers on PubMed about this technique. It's really exploding in popularity because maybe the most driving factor of all is that it's very easy to use, and it's actually rather economical to set up. So easy is a really big driving factor for adoption. This is what transcranial direct current stimulation looks on my head back when I could go into my lab. You can see there's 2 electrodes. There's those pink things on my head. There's 2 cables running down the side of my neck, the red one and a black one. In electrical stimulation, we call the red the anode, and we call in this case, the black cable the cathode electrode. And so you don't see it, but there's a little battery-powered stimulator somewhere on my lap. And a typical TDCS session is about 2 milliamps, just on the order of a few milliamps. The sessions go on for about 10, 20 minutes. Depending on the indication, people might repeat these sessions once a day for several weeks. And you'll often hear the terms nodal stimulation or cathodal stimulation. Because we always have an anode and a cathode, we know that you can't just put one terminal right onto a light bulb and light it up. Same thing with the head, you need both wires. So there's always an anode and a cathode. So when people say I'm doing a nodal stimulation, What they mean is that the brain region that they're interested in is near the anode, or if they're doing cathodial stimulation. But, but it's an important nuance to keep in mind. It's a very well tolerated technique, right? And again, this is partially why its adoption has been so wild, right? You can easily have undergraduates stimulating other undergraduates, asking basic questions about cognition and behavior. But there's also now pivotal clinical trials running for a broad range of indications: Alzheimer's, Parkinson's, epilepsy, depression, many more. But I'm not going to be talking about the clinical uses today. This notion of anode and cathode is very important to keep track of. Here you have a cartoon where you have an anode electrode and a cathode electrode. Under the anode, positive current is entering the body, and under the cathode, current as a positive quantity is exiting the body. So the cortex under the anode sees current and the cortex under the cathode sees current, but the directions are opposite, where in the case of the cortex under the anode, current is flowing into the brain, and the cortex under the cathode, current is flowing out of the brain. And it's been known for a long time, and we've contributed to this work, that this direction matters a lot. And if you imagine here, this is again a cartoon. These are neurons in your cortex. Let's say these are layer 5-6 pyramidal neurons, and you can see they're asymmetric. So they have a bigger dendrite on top and a little dendrite on the bottom. And because of this asymmetry, they polarize as shown here, where under the anode electrode, what we'd call a nodal stimulation, the soma is depolarized, while the dendrite is hyperpolarized. And because the soma is considered more important, and you may say, well, that's not true, and you're correct, but because the soma is considered more important, the anode is considered to be where you produce more excitability. Under the cathode side, the soma is hyperpolarized and the dendrite, the apical dendrite, is depolarized. And because the soma is more important, brain function is considered to be dampened. Now, this is a cartoon version for TDCS. And if you read most TDCS papers, this is still the justification given, in paragraph 2. Paragraph 1 is like why their indication is so important. And then paragraph 2 is why TDCS works. So if they want to boost a brain region, let's say there's a region that they want to heal and they want to drive plasticity, they'll put the anode over it. If they want to inhibit a brain region, let's say you have epilepsy and they want to dampen it, they will put the cathode over it. This is obviously a gross oversimplification, but it is a starting point to understand why TDCS is used. In addition to our work in animals, our work on the translational side here really started with computational models. And so we were one of the earlier groups that developed gyride precise models. And what this means is that these are models that start with an individual MRI, and we developed a modeling workflow that preserved the resolution of these scans, which is about 1 millimeter in each direction. And so, for example, you can see in the cortex that you preserve the folding. But equally important, we did certain post-processing steps that went beyond the resolution of the original scan. For example, if you looked at the scan, it might look at certain points like brain is touching skull. That's just because of the thickness of the CSF drops below 1 millimeter, it may look that way. But we know a priori that brain cannot touch skull. And so in post-processing, we do steps like ensuring that the CSF is continuous. And it turns out that both preserving the resolution and also ensuring that you don't add a level of precision that's, let's say, anomalous, or this post hoc correction, ended up being very critical for the kind of predictions that these models made, and moved us in a direction that was very different to where the field was moving at that time. So this is an example of a model of 2 electrodes on the head. This is called the M1SO, or the motor supraorbital montage. It's used a lot for pain and for rehabilitation. This is a computer model, and the model will model current as it flows through the whole head. So considering the different tissue shapes and different conductivities or resistivities, but we focus our analysis on the cortical surface, where we represent electric field in false color, as I think everyone here is very familiar with. These are the predictions that we made in 2009. What we predicted was that when you take 2 sponge electrodes like this and place them across the head, you produce a very diffuse current flow pattern. And you also produce a lot of clustering. You can see it's kind of idiosyncratic. And if you look cross-sectionally, there's really no sense of depth, in the sense that the current goes all the way through. This certainly does not look like there is anode under one electrode and cathode under the other. It looks like you're washing the whole watermelon with current. And at the time that we presented this, this was very controversial because people did assume that neuromodulation was restricted under the electrodes or even under one electrode, the electrode that you were interested in. And there's a long history of why that came about. And there's very good neurophysiology that led people in that direction. But there's also more than one way to interpret that neurophysiology. So I think the foundational experiments were correct, but I think these models are also correct. And in fact, we have now validated this in people. So these are people who have epilepsy and they have many electrodes implanted inside their head. They're undergoing preoperative monitoring. We apply TDCS to them. We can directly measure where the current flows in their head. And these models, the same pipeline from 2009 and the same values, which are, this is just, I'm not putting absolute scale here, but the maximum here is about 0.6 volt per meter for million applied. Turned out to be right, which was, I think, a pretty good guess for that time. So that was one thing that the model said. And then we said, well, if regular TCS is not focal, could we be focal? And so we went ahead and we started to play around with, propose, instead of using large electrodes, use small electrodes. And when you use small electrodes, you can put you can put a lot on the head, right? Because they don't touch each other. You can also arrange them in different configurations. And this configuration here has one, let's call it an active electrode, let's say the anode, surrounded by 4 return electrodes. Let's say they're the cathode. And so we're pushing current into one and collecting it through the others. And when we ran this model, the prediction was that doing stimulation in this way would produce much more focal current flow. And in fact, the tighter you made that ring, meaning the closer you brought these outer electrodes to the middle one, the more focal you could be. This was published in that same paper, and people also really did not like this idea. So on the one hand, there was pushback to say, well, the pads are focal. On the other hand, there was pushback to say, you cannot be focal with non-invasive electrical stimulation, with transcranial electrical stimulation, because, and I quote, the skull is resistive to current flow. And by the way, you can be focal with techniques like transcranial magnetic stimulation because the skull is transparent to current flow. And I can talk more about it, but that's not a good way to think about it for many reasons. Well, I will talk about it. People think that the skull diffuses current flow, but actually it's the one place that it doesn't. When current enters the skull, it just wants to get to the other side. It's not going to flow sideways, right? It's going to flow through, right? And so just because you have a resistive medium doesn't really mean that things disperse. What really matters is the fact you have multiple layers, and those layers have different conductivity. But in any case, when you do a 4x1 stimulation like this on the head, it's focal. Actually, you can also do 4x1 on your cat, on a table, on the wall. It doesn't matter. The current's going to stay between the electrodes. There's no reason why the current would take the long way around. This was also pushed back against. This was also validated in various forms, but we did need, it was an uphill battle to do so. And that's fine. When you show models, people should not believe you. Another good feature of this that we suggested was that it was more unidirectional. Where large pads, you have both the anode and the cathode, and so you're always thinking about both of them. Here, if you have, let's say, 2 milliamp flowing through the anode, you have negative 0.5 through each of the cathodes. So there's sort of a dispersion, right, where it's like a 1 to 4 loss. But actually the dispersion is even larger because of the way the current ends up wrapping back across the whole head. So it's not unidirectional. All current in must come out. But it looks unidirectional when you plot it this way, and we think that there's reasons to think functionally it might be more unidirectional, which is appealing as well. I talked about the translation, and that's really, that's a separate talk, but I did want to say, it was a long road from 2008, when I would say the idea was invented. Or by invented, I meant that a graduate student came up with an idea and ran a computational model. People didn't believe that you could be focal through the head. People also didn't believe that you could stimulate with small electrodes. People were using these large sponges because they thought they were important for tolerability. And when we said that we could stimulate, we needed to stimulate through small electrodes, their response was that that would not be possible. It wasn't possible. It was not possible until we engineered the electrodes that could do this. That was done in the laboratory. We also ran some pilot clinical trials in healthy subjects, looking at tolerability and so on. But at some point, we got as far, and then the clinical community started to notice. And so pain doctors depression doctors start to ask us about this technology. And at some point, it was no longer appropriate for those activities to continue in the lab. For example, graduate students should not be doing customer support, or something like that, or production for that matter. We looked at different ways to commercialize it, and we ultimately, in this case, formed a startup called Soterix Medical, which it was a medically certified company. Until recently, it was the only ISO, I think, medical certified company in Manhattan. I say recently because this past weekend we moved to New Jersey just for more space. The company supported a lot of the necessary productization steps. You'd be surprised how hard it is to get the right kind of cap. You know what I mean? And the nuance of whatever it is, going from 3D printing to injection molding and all the quality systems, and then supporting a wide range of clinical trials. And so Soterix Medical Technology now has been probably trialed in about probably 200 papers. Clinical trials have been published across a variety of different indications, and it's used in hundreds of medical centers. It is approved around the world for different indications, pain, neurorehabilitation, mood, but not in the U.S. yet, or not for neuropsychiatric disorders in the U.S. yet. I'm happy to talk more about that if it's of interest to the group, but I was going to take a step back maybe and talk about the modeling a little bit more, because it did all start with the modeling. And the only reason we're able to do everything that we did was because we developed a slightly better model than existed before. And so it's that's the example, a graduate student just doing something a little bit different. And then there is, decades of impact, right? There, you know what I mean? There's dozens of people who work in this company or work in hospitals that work with the company. So it's a huge impact just from a graduate student having a smart idea and following it through. So these were those computational models. And from then to this day, we know that what makes a good current flow model, I should say these are current flow models, they don't model neuron responses, is you need to segment the tissue to the right bits, the skull bit and the CSF bit and so on. And you need to assign the correct conductivities, such as the skull is very resistive and the CSF is very conductive, right? So you can see that here in the conductivity in Siemens per meter. And if you do that right, you will predict the correct current flow pattern. That's really all there is to it. And you need the right level of precision. That's why this paper was so impactful, not just in establishing focality, but in establishing a modeling pipeline. And since then, additional grad students in my lab and myself have been very busy, I would say putting icing on the cake and trying to optimize this process. And if I would highlight, I think where we're the most innovative and significant steps. One was this paper led by Jacek Dymachowski, who's now a professor actually in my department. Instead of modeling different electrode positions, is this one better? Is this one better? Is this one better? The idea was to start the other way around and say, well, I would like to get current to this brain region, this ROI. Where is the optimal place to position electrodes? And it turns out that this was because the problem is inherently linear. The current flow here plus the current flow, you can add up sort of the lead fields from each electrode. This problem was very tractable, and so this paper I think presented a very elegant solution to it that has been built on since then. I mentioned the validation. This was so important. For a very long time, I would give talks, and afterward they would just say, well, it's just a model, it's just a model, it's just a model. I'm, by the way, an experimentalist by training. I came to that paper I published in 2008 was the first modeling paper of my career. So it's funny for me to be on the other end of it, but I respected it. It was and there's been a dozen validation papers, but it wasn't until we did this one that things were so clear. There's also a lot of attempts to optimize the modeling process, to democratize it, to make it not require very expensive engineering software. One of those contributions was Roast. This is something that you could download on your laptop before I'm done with this talk. And if you have your own MRI, you can segment it and run a current flow model on your own MRI before I'm done. That first model I showed you in 2008, it took the grad student 3 years. I'm not exaggerating. It took them 3 years to run one model. to figure out how to run the one model, right? Now it takes you 3 minutes. But I also want to say that in a sense, for all this work, nothing has changed because we're still following the exact same pipeline that we sort of came up with in 2008. And so as an example of how not innovative we are, let me show you the most important change we made in our pipeline in a decade, how not innovative we are. So in this paper, a long story short, we realized that the space between the brain and the skull was not cerebral spinal fluid. It's not cerebral spinal. There is some cerebral spinal fluid in there, but there's a dura mater and there's pia mater and there's meninges, and even the CSF is not pure CSF, right? There's different stuff in that space as well. And so really, this really critical compartment that really determines focality and current delivery was not being modeled correctly. It should have been modeled with all these different layers. The problem is that you can't model all these different layers, not tractably in our existing pipeline. It would just create a very massive model. And so our proposal that we validated in this or verified in this paper was to keep it as one compartment, but not to call it CSF anymore, but to call it emulated meninges. And instead of assigning it a very high conductivity, we assigned it a more lower conductivity. And this paper was published. And from then on, this is very recently, we've changed our modeling pipeline in this one tiny step. So that's just to illustrate one, I think, an important idea, but also talking about a decade of no innovation, where at least in my lab, we're doing something very similar again and again, but we thought with high impact because we're deploying it in different ways. I want to say a little bit, therefore, about a new computational current flow that we're currently working on. So a difference from how we and others have been doing it for a decade that I think will be interesting to unpack. The way I came to this wasn't through TDCS, but through electroconvulsive therapy, which for a long time was not something I was at the top of my list of things to work with. People who work in electroconvulsive therapy tend to have their own sort of lane, even if they cross into other people's lanes, and people in other lanes tend not to cross into the electroconvulsive lane. But for those of you who don't know it, it is an incredibly effective technique for people with very severe neurological and psychiatric disorders that have failed to respond to other things, like they're suicidal. ECT for many of them is literally a lifesaver, and improvements in the technology have really reduced a lot of the associated cognitive side effects. So in some cases, they're mediated. ECT, the people are anesthetized and electrodes are placed on their head. These are different montages. They call them RUL for right unilateral, BL, bilateral, BF for bifrontal. So electrodes are put on the head, just like with TDCS, but from then on, the similarities end. Whereas TDCS applies 1 milliamp or 2 milliamp, ECT applies almost an amp. And like with other neuromodulation technologies, applies a series of pulses. In fact, they keep pulsing or increasing the number of pulses they give you until you have a seizure. And you're anesthetized, but they can monitor that seizure while you're out. And it's current controlled, and so the voltage is increased to provide the right amount of current, and as a result, you have an impedance, so that the current applied times the head impedance gives you a voltage. And so the devices report what they call a dynamic impedance, the impedance during stimulation. The impedance is also measured before stimulation. So while they're setting you up, they're measuring the electrode impedance. It's very common in neuromodulation to check impedance to make sure the setup is good before you do the ECT. This is done with a low level of current because this is not the time to produce a seizure, about 1 milliamp, a very high frequency. And with static impedance, the head resistance is 500 ohms. So the head impedance has changed from 500 ohms to 200 ohms. It's 500 ohms to 1 milliamp, but it's 200 ohms to 900 milliamps. So these values vary, but it's been known literally for decades that the head impedance varies depending on whether you're measuring during the 1 milliamp current application or during the 900 milliamp current application, which is why they called one thing static impedance and one thing dynamic impedance. And the explanation for this is that the impedance of the head is changing based on the current that you apply to it. So in response to 1 milliamp of current, the head shows a certain impedance, and to 900 milliamps, the head shows another form of impedance. And the simple explanation for that is that tissue resistance is changing in response to current flow, that when you apply 900 milliamps, the resistance of the head decreases. The current is changing the resistance of the head. Now, if you were to model that, we would need one of two things. Either we would need two models. We'd do a 1 milliamp model and a 900 milliamp model, and you would just set them up differently so that the 900 milliamp model had a 200 ohm resistance and the 1 milliamp model just had a 500 ohm resistance. That would be the conventional pipeline. But a different pipeline would say, well, why don't we actually model the current changing the resistance? So you apply a current, the current goes into the tissue. As the current flows through the tissue, it changes its resistance. It's a little bit complicated because if the current then changes the tissue resistance, well, now the current flow pattern will also change, right? Because the tissue resistance has changed. And so there was a little bit of work that had to go into this. In this case, it didn't take us 3 years, it took us 2 years of a graduate student's time. And it's what we call adaptive tissue modeling. And this was published, so let me just present the idea briefly, and then if there's questions, I'm happy to go back. But once again, we start with MRI data. In this case, this is data from patients who actually underwent ECT. And so from each one of these patients, we have their clinical static impedance measured at 1 milliamp and their clinical dynamic impedance measured at 900 milliamps. So we have both impedances and we have their MRI. We segment it. One thing that's a little bit different here is we divide the scalp into 2 layers, a superficial layer and a deep scalp layer. And there's a long history of modeling the skin and thinking about the skin as having different layers that respond differently to electrical current flow. And so we're building on it. Other than that, much of the workflow was the same. You can see we have the meninges layer instead of the CSF layer, but that's that one compartment. We use FEM, lots of elements. I just want to mention that just the skin itself can have millions of elements. And so the first thing we do is we simulate current flow. So we take all the tissue conductivities, we sort of assign them, and we take all the tissues, skull, CSF, so on, we assign them conductivities, and we simulate the kind of current flow that you get. Now we do this for 1 milliamp, and we also do this for 900 milliamps. And so obviously for 900 milliamps, you'll get more current flowing through the head and you'll get a bigger electric field. And what I'm plotting there is the electric field on the surface of the skin, not the brain. So we get an initial prediction of the electric field on the surface of the skin, but this electric field is then modeled to change the conductivity of the skin, and particularly the conductivity of the superficial skin. We assume that the deep skin does not change with current flow. Only the superficial skin changes with local electric field. This is the function that we developed based on the literature and our own sort of intuition. Essentially what it says is that for very low electric fields, you start with a sort of minimum scalp conductivity. And then at some threshold, as the electric field increases, so does the scalp conductivity, but up to a limit. So at some point, the scalp cannot be any more conductive. So there's a saturation point. And this behavior was very important. So now what we do is we go back to the model, right? And we reassign new electrical conductivity to each element, to the millions of elements. Each element now has its own conductivity. So what you're seeing there is a plot of the conductivity. Even in the 1 milliamp case, you see this ring of increased conductivity. It's a ring because the current is concentrated around the edges. While in the 900 milliamp case, you see there's a rather a more intense and a more distributed increase in conductivity. So now all the conductivity has changed, but because the conductivity has changed, we now need to rerun the current flow model. So now we have a new sort of new conditions, right? The scalp is no longer one conductivity, as higher conductivity here, lower conductivity here. So we remodel current flow, so we get a new current flow pattern. But if there's a new current flow pattern, that means we also need to reassign the conductivity. So you can see this is an iterative process, and it runs a few thousand times until the model converges. Now, when it's converging, we're sort of done. We end up with these 4 final pictures, but we also end up with a model prediction of static and dynamic impedance, meaning in the 1 milliamp case, right, the model can tell us what was the impedance of the head, what's the voltage divided by the current. And in the 900 milliamp case, the model can also tell us what is the predicted impedance, right? So we actually predict the impedance that will be measured by the device in each condition. And we happen to have those data from the patients, right? We have the clinical static impedance and the clinical dynamic impedance. Now we have the model static impedance, the model dynamic impedance, and we ask if they match. If they don't match, and they usually will not on this first run, we go back into the model and we adjust two parameters. The first parameter is the conductivity of the deep skin. This is a single parameter. It's not electric field dependent. And the second parameter is the maximum conductivity of the superficial skin. Once we reinitialize it, we run this model again. It iterates, it converges, it predicts a new static and dynamic impedance. And if the predicted model static and dynamic impedance matches the clinical case, then we're done. Now, if you're saying, well, you have two free parameters and you're fitting two data points, this doesn't seem like such a hard problem. It was. Okay, there were many technical reasons why this was difficult. We had to keep a lot of these values within a physiological reasonable range, right? We didn't want to assign like the conductivity of metal, you know what I mean, to some cases to make it work. And so yes, in retrospect, everything is easy, but to get to this point, and it was also computationally very hard to get to work, but we got it to work. And again, for each head, we assign a subject-specific deep skin conductivity and a subject-specific maximum skin conductivity. And this is important, right? So each subject has their own anatomy now, but they also have their own unique skin properties. My skin and Jean's skin is not the same. And specifically my superficial skin and my deep skin is not the same as Jean's skin. That's the only way we can get these models to work. Head anatomy was not enough to predict individual differences. We had to have different skins. That was the only way we could match the clinical data. And so this was this adaptive tissue conductivity in a very short introduction and the publication, and which we'll hopefully submit formally. The preprint is here. What do these results look like? Oh, please, Gene.
Sorry, speaking of my skin, why is it changing conductivity? What is the reasoning behind it?
There is a lot of literature going back to the 60s, skin conductivity changes with current flow. So as it was an observation that was very well known. And since the 60s, 50s, people have been trying to figure out why. And the shorter answer is, I think, it's not clear. The other answer is, there certainly have been hypotheses. One of them includes sweat pores. So current tends to concentrate through sweat glands, or because they're very conductive. And this notion that as current flows through them, they will actually open up and therefore allow more current to go through. Electrical stimulation also activates blood flow. So it's a classic, you get skin redness, which will also change conductivity. So there are different ideas of what causes it. And there's been different models, lump parameter models, resistors, capacitors, that have been implemented to model it. I personally think that the jury is still out on what's really underpinning it. And so therefore, the relationship that you see here that we settled on, I would call it a heuristic, empirical, sort of matches what you would see across the data. And by the way, we only have two skin layers. And in reality, I think there's 10, and then there's fat, and then there's connective tissue, and they're all responsive to current flow in a different way. We threw all that out. So this is a gross but effective assumption. And in this paper, you'll see we actually validated it different ways. So we had different sets of data that we used to validate it with different experiments. I feel okay about it. This is an example of what it might look like. This is a subject who received ECT. There's their clinical static impedance data. There's their clinical dynamic impedance data. Here's the modeled static impedance data and the model dynamic impedance data, which only came about because we assigned the subject a specific deep skin conductivity and a specific maximum superficial skin conductivity. So those values are important. This is what the plots look like. Now we're plotting skin conductivity and skin electric field. And then there's also ultimately the prediction of brain current flow, which is ultimately what you're interested in. But in this paper, we were really obsessed with what was going on at the level of the skin. And then, obviously that would then change what happens at the level of the brain. And you can see there's, you can see in the skin conductivity values and in the skin electric field values, there's some order of magnitude differences, right? There's much more juice in the high current case. And here's a different head. And I don't mean to get any more into it than just to say, you can see that this head not only has a different anatomy, but has different skin properties that lead to predictions that we think match the data. This is how we approach this problem. And again, a lot more details in the paper. You can do fun things with the model. You can tear off the skin of one model and put it on the other head. And we have 2 layers, so we can manipulate these things in a model. We can ask various questions like, well, what's the importance of skin versus head, right? So if I have one impedance and Gene has another impedance, how much of that is because of our skull shape versus our skin properties? Because now I'm saying skin properties are different. So I could tear Gene's skin off and graft it onto my skull in the model, and I can run that simulation, right? So obviously it'd be very hard to get an IRB to let you do that in college kids, but we could do it in the models. And I really will just refer you to the paper, but you can look here in the black. This is clinical data. Each one of these black points is a subject. And you can see that each subject has a different static impedance and a different dynamic impedance. The error bars is because they're getting multiple sessions. And generally you can see that subjects with higher static impedance have a higher dynamic impedance, but it's not quite clear. In the false color, what you're seeing are these skin swaps. So we have superficial skin, we have deep skin, we have different head shapes. And so we're mixing and matching them. There's a lot of combinations, and then we can get a prediction in these simulated heads about the relationship between static and dynamic impedance. I will refer you to the paper, you know what I mean? Because I think some of these questions really get maybe more exciting if you care about electroconvulsive therapy, and they may be less exciting to you if you care a little bit less about electroconvulsive therapy. But they teach us things, like the importance they teach us very interesting things. But I want to get back to, and Cynthia, when should I'm sensitive to time, when would be a good time to stop?
Maybe you could go 5 more minutes, so we have 5 minutes for questions.
Perfect. So in the last 5 minutes, let me bring this back to TDCS. And I think this is interesting technically, but also for the junior people in the audience. It's also interesting how going down one road sometimes brings you back to the other road. So working on a field that you think might be different than what you really care about teaches you something so important about what you think is your main field. And so what does this teach us about TDCS? Because TDCS is 2 milliamp and ECT is 900 milliamp. And I just told you that the 900 milliamp case is not like the 1 milliamp case, right? And the thing is, as we were working on this 2 years ago, something was bizarre, and it bothered me, and it kind of bothered all of us, which was this. The skin conductivity under the 1 milliamp case to match the data, it goes up to, you can see it's a fraction of a Siemen per meter, right? Or like 0.03 Siemen per meter, right? While in the 900 milliamp case, the current goes up to about 0.4 Siemens per meter. So that's what we thought, that only when you get to 900 milliamps of juice, does the skin conductivity cross to about 0.4 Siemens per meter. But in the TDCS literature, starting from our work, and with few exceptions continuing through every modeling paper, you can see that the skin was assigned a very high conductivity value. Why did we do this initially? I don't know. Maybe we made a mistake. Maybe we were really smart. Maybe we were lucky. But we assigned a skin conductivity to the TDCS models that was very high. And maybe it was just we thought, oh, skin can't be more resistant than skull. Turns out the superficial part of the skin is. But at that time, that didn't make sense to us. So we said skin must be somewhat conductive, right? It seems like it's kind of salty and wet. So we assigned this high value, and that's been the case, and that's what's been validated. So this seems like a correct value. In fact, I didn't show you all the validation, but we've done tons of different validation, and the models with this value seem to make sense, but it doesn't make any sense because it means that in TDCS, we're using ECT 900 milliamp conductivities, and the short version is that the reason we think that is we think that during TDCS and TACS, the skin conductivity is already changing. How could it be changing if it's such low current? One peculiar feature of TDCS, and also, by the way, TACS, another related to TDCS, it's applied for a long time. It's that DC is on, but it's not on for 1 second. It's not on for 10 seconds. It's not on for 1 minute. It's on for 10, 20 minutes. And there's old reasons why they do it this way. So it's not 1 milliamp for a millisecond. It's 1 milliamp for minutes. And we knew from other experiments that during TDCS, the skin impedance changes. So what you're looking at here is an average across a bunch of healthy volunteers. We're applying TDCS on the head for 1.5 milliamps. And you can see in the blue trace is the voltage. And the voltage just go up initially because the current is ramped up. But then you can kind of see that even though we're at a fixed current level, the voltage starts to drop. And that is because the impedance is dropping. And so, and we looked at this for very different reasons. We're looking at like low power TDCS stimulators. We thought this could have some safety. But when we look back at this data and other people's data, it became obvious that head impedance changes during TDCS. And it's not just the electrode. So we thought it was important for device design, but it shows adaptive tissue response. So it may be that what's happening is that if you do 1 milliamp, but you do it for a minute, the skin conductivity increases. And now you're in this regime of 0.46, but it's still not quite the same because it's only under the electrodes. And so, and I think there's some mechanistic insights to be drawn here as well. And so now we're going back to our TDCS and models, and we're adding these adaptive features that we plan to. And we will see what we learn, right? And we'll see how much of a difference that is. All right, I'll just say a few final words about neural networks and oscillations. It's something that we think a lot about. I know some people here think a lot about it as well. We're very interested in them in targets of electrical stimulation. Electrical stimulation, we know, will polarize neurons and affect neurons, their somas and their dendrites. We know also that electrical stimulation will affect synapses. Electrical stimulation loves axons and loves axon terminals. So terminals are also polarized as well. But when you have a whole bunch of cells connected by a whole bunch of synapses, you get a network. And these networks can, under certain conditions, become active. They become coupled. You get emergent network properties, most obviously oscillations, right? Alpha, gamma. So these networks are now oscillating. So now you have a big cluster. And we've studied for a long time, right? This is a slide from, it's a decade-old slide, that these networks are very sensitive to electric fields. And by the way, when I say adaptation here, I don't mean conductivity adaptation. I mean the network is adapted. What you're looking at here is a spectrogram of oscillations in a brain slice. And what we call gamma in a brain slice is about 25 hertz. We turn on fields of either the anodal or the cathodal variety, anodal being positive and cathodal being negative. You see that there's these interesting transient effects when you first turn them on and off, but you also see that during the field itself, there's a change in power. So during a nodal DC, we have more power, and during cathodal DC stimulation, we have less power. And what we found is that these networks were more sensitive than we would expect based on an individual cell sensitivity. So this led to the notion that networks are more sensitive. And that was published quite a while ago. One last paper I'll bring your attention to, and then I'll wrap up then, is a recent work that just appeared in Brain Stimulation, where we looked at temporal interference stimulation. This is, an area of neuromodulation, like some pretty, hot stuff, right? That came out of just a few years ago from a group in MIT. They sort of rediscovered or reapplied an old idea. And that old idea is that you take two stimulators, both at kilohertz frequency, but slightly different kilohertz frequencies. Let's say 1 kilohertz and 1.005, or 2 kilohertz and 2.1 kilohertz. And so you stimulate with two separate pairs of electrodes. And somewhere and they both produce an electric field. This one will produce a 1 kilohertz electric field, and this one will produce a 1.0005 kilohertz electric field. But in the middle of the brain, these electric fields will collide, or they'll overlap with another. And that will produce a resultant amplitude modulated electric field. So it'll still have a carrier in the kilohertz range, right between the frequencies of the two carriers, but its amplitude will increase and decrease. This was this old idea called interferential stimulation. They called it temporal interference stimulation. What you're seeing here is a computational model of temporal interference stimulation. And we're plotting two things. One, in the Bono case, we're saying, well, if we just look at the unmodulated component of the electric field, right? So the electric field where it's largest, where is that? And that's on the cortex. So that's nearer the two electrodes. It's where you have the most juice. And so you're producing the biggest electric fields there overall. But if you ask, where is there this collision happening, or where is the electric field amplitude increasing or decreasing the most? So how much amplitude modulation you get? It turns out that you can get amplitude modulation deep in the brain. So you can produce amplitude modulated kilohertz stimulation selectively deep in the brain. And this gets people very excited. under the assumption that the brain will be sensitive to the amplitude modulated kilohertz stimulation and not to the unmodulated kilohertz stimulation. Because if they're sensitive to both, then you can, A2, you're stimulating the periphery, A3, you're stimulating the middle. And so we in this paper, we looked at this and we fell back to our classic computational model and brain slice tools. And what we found was this. Here again, you're seeing the same spectrogram. These are ongoing oscillations in a brain slice. I should say hippocampal brain slice. This oscillations are pretty stable, and then we apply stimulation. When we apply low frequency stimulation, so this is 5 hertz, we've been doing this for a long time, you can see that the oscillations are modulated. They come and go and they come and go, depending on the phase of the stimulation. And this is something we knew for a decade. When we applied amplitude modulated kilohertz fields in A2, we saw something kind of similar. They come and go and come and go. But if you're looking closely, we needed 80 volt per meter in that case to produce actually a smaller modulation effect. So we could produce the same amplitude modulation. And the amplitude modulation was at what they call the beat frequency. But we need a lot more juice. Now, when we applied unmodulated stimulation, so just straight old kilohertz stimulation at comparable high intensities, we also saw modulation, but it was not a beady modulation. It was just a general boost. There's a couple of things happening here. We're changing the carrier and all that, but the paper looks at the full dose response. And so what we said is that amplitude modulated kilohertz stimulation will work, but you need a lot of juice. And that same level of juice will produce an unmodulated field, right? That will also affect things. And models allow you, then this was experimental data. We were then able to generate a neuronal network model that reproduced this data. And then we took it a step further. We played around with that neuronal network model. We played around with things like the time constant of the individual cells, as well as whether this network had GABA B synaptic transmission or not. And again, to make a long story short, what we found is that we believe that when you do temporal interference stimulation, you can't affect just the deep brain without affecting the periphery. Any kind of situation where you see, so what you're seeing with dynamic modulation is where the oscillations are getting bigger and smaller, bigger and smaller. And static modulations are regions of the brain where the oscillation just got bigger. So if you look at C1 with GABA B present, you can see that at 83 milliamps at each side, 83 and 83, you are able to produce dynamic modulation just deep in the brain, which makes sense because that's the only place where you have amplitude modulated electric fields. But you still have static modulation in the outside of the brain, which makes sense because that's where you have unmodulated electric fields. And you can fool around with time constants and GABA, but C1 first column is really the best case scenario. And so we predicted that temporal interference can work, but at least based on our assumptions, it would require substantially more current than is used for TDCS. And you would still need to contend with the fact that you are affecting the periphery of the brain, I should say, but in a different way than you're affecting things centrally. And there has to be some sort of differential value to those things. Or our models are missing something very essential that would make temporal interference work in a way that we cannot see. And so, there's translational, by the way, work they're testing temporal interference as we speak on different clinical indications. And so again, here's modeling slice data and it's chasing clinical applications, like instead of doing deep brain stimulation where we implant electrode deep in someone's head, can we do temporal interference stimulation and target that deep region? Very ambitious goals, very exciting. And here you can see how we're applying our tools to inform it. So I took more than the 5 minutes you said to allow, but I did want to sneak that in, and I'll finish there, and I'm happy to take any questions.
I'm going to clap for the whole audience. Thank you so much. That was a really exciting talk, and you raised at least 5 different topics that I have a lot of questions about. So I think I'll say everyone's free to leave because it's 3 o'clock. And as long as you have time, let's stay on and answer whatever questions anybody has. So I guess I could start. I'll just go kind of back to earlier in the talk. And I was curious, when you're developing your HD TDCS technique, how many different foci could you create externally and successfully focally stimulate different sites on the brain?
So I think you probably have good intuition on the answer based on the question. So it turns out that with a 4x1, you could do another 4x1. So you could have two 4x1s, and people have done that. So you could have, and they can be different values. You could have an anodal excitation here and an anodal excitation here. You could do a nodal on one side, you could do cathodal on the other side. What I didn't mention is that you can actually do, you can also do any waveform you want through these. So there's something called transcranial alternating current stimulation. And so people can also do AC stimulation on one side and AC stimulation on the other. They can do different frequencies. They can do in phase. They can do anti-phase. So people have been actually fooling around with different aspects of this already. So in principle, you can go to multi situations. And also you're not limited. Theoretically, you can have 20. I think there's like 60 channel high definition stimulators. So theoretically, you could energize each electrode with a different amount of current and create a very nuanced pattern. I think sometimes people get too fancy for their own good. And so when they start talking about stimulating 13 different nodes in 13 different ways, it's like, oh, that's really ambitious. But I think generally speaking, 2 ROIs, it seems quite meaningful and tractable.
Okay, thank you.
Hey, Marom, I have a question about your anodal model at the very beginning. And, there's something called anodal block. So this sort of contradicts that idea. And I'm assuming this has to do with your assumption here that this is anodal stimulation at the soma versus anodal block maybe working at the more linear nerve. Do I get it right? Or would you like to correct what I'm thinking?
Your thinking is correct. And I think it's a matter of scale. So what I didn't say is that TDCS with 1 milliamp produces about a volt per meter of electric field, which is about 0.1 millivolt of polarization. So when I'm talking about depolarization here, I'm talking about a 0.1 tiny amount of depolarization on top of it. So that would be still an anomaly excitatory regime. And so for depolarization block, I guess I would need to apply 100 milliamps at the skull to produce 100 volts per meter to start to produce that much. And so that's why I don't think we're approaching, I left that out, but that's why I don't think we're approaching the depolarizing block regime, because we're so low intensity, which is also why, by the way, a lot of people don't believe in TDCS, right? They say this is so low intensity that I don't think it can meaningfully modulate activity. So that brings us back to oscillations, because oscillations are very sensitive to fields.
Thanks. And the interference stimulation at the end you presented is really amazing. It's really out of the box. So good work.
Are you a believer?
No, I think it's very intriguing. I mean, you're going to get the same crap about where it's a model, but show the data, all that. But I think it's really intriguing.
So I have a question. What can you do functionally with this kind of modulation of oscillations? Like, are there any clinical experiments or neurophysiological experiments, behavioral experiments that kind of address that?
So the notion that you could obviously modulate oscillations with stimulation, that's been around for a long time. And I'm going to give you the hand waving answer. You know what I mean? The hand waving answer that people think that oscillations are important for, as you know, for a lot of things, right? And they're important. Cognition is gamma, and having a good night's sleep is slow wave, and all these things. And so people associate, and when you have diseases, people say you have depression because you have too little alpha, whatever it is, and the mismatch. So oscillations keep coming up, and that's both very popular opinion and an opinion that has very strong pushback against, including, by the way, people like Buzaki, who was instrumental in identifying these oscillations, who pushes back on like the phrenology of oscillations. But they're low-hanging fruit as far as target. I also think, by the way, one reason they're very low hanging fruit is because they're so obvious. It's like the most obvious thing you see. So, if it's what you see, it's what you're going to focus on. So I think that's where it starts. And so people say, this is my target. And I'm going to treat schizophrenia with TDCS, and my target is gamma. And so that's going to be my target engagement. And so people gravitate to that idea, and people also gravitate to the idea that if I want more alpha, I should stimulate with more alpha. And if I want more gamma, I just stimulate more gamma. And there is some sense to the idea, like if you look at this paper that is being cited here, there's some sense that when you add, if you match the frequency of the endogenous oscillation, you need less electric field to impact it, right? But you can't really create something from nothing. You know what I mean? And I often take the analogy of, like, let's say your screen refreshes at 60 hertz. If you bang on it at a hammer with 60 hertz, it's not going to get brighter. So just because you match two frequencies doesn't mean you're going to get a benefit. But that's another way where people are really into oscillations. And so I haven't answered your question, because for me, I think I'm very confident to say that oscillations are very sensitive to stimulation. And when you have and I'm also confident saying that when you have an oscillating system, you can't understand what stimulation does without thinking about the system as a whole. But linking that to clinical outcomes, I think, is really worthwhile. I don't want to sound like I'm poo-pooing it. I'm not. I think it's extremely worthwhile, but I think it may not be a simple story as sometimes people make it out to be. But there are great stories.
It just seems that oscillation is a part of, almost any story, right? Like you said, it's present all the time. So it's part of the way the brain works, but it's almost like this whole concept of stimulating the vagus nerve, right? It's like the one pipe.
Right. Right. I like that point. Right. You could no stimulation that affects the brain will not affect oscillations. Right. And so you're going to find it. If you have any effective stimulation will somehow show up in a change in oscillation. So yeah, you're right. It's ever present.
Thanks.
I have a question. Can you hear me? Oh, okay. Nathan Crone here. So I guess we generally avoid direct current stimulation intracranially because of charge deposition and things like that. But has anyone, what has been done in that respect? Because it seems like you could overcome this question of the focality of stimulation pretty easily that way.
Yeah, so I'll let Gene, as far as I know, is, if not the only, certainly the pioneer in invasive DC stimulation. And so that's really that expertise you have locally. I know. Gene, I don't know if you wanted to.
Oh, we should talk.
Okay, yeah. So Gene is the guy.
Absolutely, yeah. Nathan, I'm happy to discuss this. Yeah.
And I'm very excited. What I will say is I'm very excited for that work for exactly the reason you mentioned. That first of all, if you could be invasive, you could be focal. But I think more than that, it opens up. And I used to not like implanted stuff because I was like, well, why would you if you could be non-invasive? But the beauty of implanted stuff is people can take it with them.
Plus,
you could stimulate for long.
Anyways, yeah, that's the other.
Yeah, so there's many advantages to potentially invasive system, even separate from the focality. And so to implement an invasive DC system is would be a huge opportunity for a range of indications.
Yeah, the other mundane thing, I guess, from terms of clinical translation, is that I think most patients don't want to have to. I don't know. I can't speak for most patients, but they don't want to wear something on their head. We've seen this with seizure detection systems. People don't want to wear EEGs, EEG electrodes on their head all the time, and it takes a fair amount of maintenance and so on. So having something implanted and sort of set it and forget it, I think has some power.
Yeah, I agree. And on the other hand, for TDCS and other things, we're working very hard to make them more user friendly, and because you may think, oh, this person has so much chronic pain, they want to kill themselves. Surely they'll wear this for 20 minutes a day. Maybe not really, because they have other things to do. And so whatever you can do to help them use it. And that's something I learned a lot. In fact, a lot of work I've done recently is on regular TDCS, not high definition TDCS, because we do not have home-based self-applicable high definition systems. And this, by the way, COVID has really accelerated home-based neuromodulation, and so this has been pad-based. This has been sponge pad-based, home-based TDCS.
So unless there's any more questions, I was going to just add one more. So I guess one of the reasons I think a lot about the number of external foci you have and maybe what's going on is because on the invasive side, there's been a trend where people go for, largest number of electrodes, smallest space. So I guess I was just curious, there obviously have been a lot of successes with DTCS for things like depression and certain other things maybe you could talk about. Do you have any idea on this larger ROI scale, what TDCS might be doing to those circuits that's advantageous at that level?
I know obviously on the invasive side, people have gone for higher density, right? More electrodes, directional leads. I mean, there's been work like at a Nitish's lab, other labs, you have locally where they've modeled and developed some of this stuff. I would, first of all, I would say the jury is a little bit out. If in all cases more is more, and one of the things that tells you that is most invasive, clinical technologies, the programming technique is still what they call like poke and hope, right? Where they kind of the neurosurgeon points at the brain and that's where they stick it, or the anesthesiologist. I'm not trying to be, again, I'm not trying to be dismissive here. Obviously, there's a great science and it's a great technique, but they're poking around. They don't know who's going to respond or what they're going to respond to until after the fact, right? So how can you necessarily tell me that having 100 contacts is going to be better than 5 contacts if you can't tell me beforehand how, whether they're going to respond to a bipolar or tripolar? In fact, I think having more leads, it may matter as much to having more span, right? As in, like, you don't know what you're doing. So, or or even, it's almost like you don't know what you're doing. So you kind of want to have more shots on goal, maybe than simply, I'm obviously dismissing that work, and but it's an area I work in, and so I don't think more is necessarily always more. And I think I've seen that also with non-invasive, where people say, look, we do have non-invasive HD systems now that can do 32 channels. In each 32 channel, right, can be independently controlled. But what do you do with that information? I mean, do we really believe that we understand? We can parcelate, let's say you could target 30 ROIs. Do we really think we understand depression with such nuance that we can parcelate the brain into 30 ROIs and prescribe how much current could go into each one? Do we really think that these brain regions are not so connected to one another that we can't remodulate one, we never really modulate the other, right? And so we're actually modulating 30 nodes, and each node is talking to each one of the other nodes. And so I'm agreeing what you're saying, that I support that work to be more and more ambitious, and we can't just be using 2 sponge pads for the next 50 years. But I think it's really hard, and we're dealing with a black box, and we want to have models. We want to have preclinical models that a priori inform us how to do things, right? Because we don't want to do poke and hope, I hope I didn't say anything wrong. I'm a strong believer in implanted neuromodulation. I work on implanted neuromodulation. I'm supported under implanted neuromodulation. I think these techniques are incredibly sophisticated. They've had a huge impact on people.
No, I think it's wonderful. Part of the point of TNT, I think, is to have these candid conversations with different people working in the field. So thank you for just sharing all your opinions and your thoughts. It's really great. Does anyone have any other questions?
I had one question.
Sure.
So you mentioned that DCS is recently sort of exploding in popularity and work. And I'm curious what you think sort of the future of the field is headed.
You're talking about non-medical uses of TDCS?
Either way, medical, clinical, or sort of non-medical.
On the medical side, I think we're getting now to the stage where we're getting these larger, what would be called pivotal, definitive or phase 3 trials. And I think those are going to be really important. These include very large trials for like age-related cognitive decline, Alzheimer's. It's something I'm very, very interested in. So we're seeing larger trials there, larger trials in pain, and some ongoing large trials in depression. And so I think those are going to be very important to convince people, both within the community and outside the community, that there's a there there. You know what I mean? And so that has to happen. Meanwhile, the clinical use there already is clinical programs, right? NYU here in Boston, MGH, Harvard. I don't know if Johns Hopkins has a clinical TDCS program, but that ship has also sailed where there's enough patients in need and enough signal there that doctors are already prescribing this off-label. So that is an emerging area, and that is largely leveraging in our home use. So for example, you go to NYU and you go to Lagoon Health, I think I'm saying it right. You go to their neurology department. I love that there's a door there that says TDCS. And so I'm so excited. Oh, there's a TDCS room. And you open it up and the only thing in it are people sitting at terminals. It's like a telemarketing thing. And they're dialing in because their entire neuromodulation program is almost entirely home-based. It's all they're doing is they're scheduling appointments, they're logging in, they're giving them cognitive therapy, they're testing out that they can do the TDCS, and it's all fully automated. I think that is a really exciting new frontier, right? And by the way, these devices are smart enough where they're monitoring and they're doing assessments as well. So there's just and then theoretically you can download a new therapy to a person. You can adjust things in real time. For me, that is a really exciting frontier. And again, with COVID, all that has accelerated aggressively. So now there's depression trials at home. There are also trials on neuro-COVID and actually more specific things there as well. So I think that's exciting, and there's a lot of technology optimization there. There's a lot of work for engineers to make devices that can be used at home, not just to do the stimulation, but to monitor people, to know how they're responding.
Okay, so it would be fair to say that it's moving more away from the hospital and into people's homes, sort of.
I mean, certain things like, Cynthia had this point about sophistication, right? So in the research lab, we're seeing multi-channel high definition integrated with EEG, TDCS in the scanner. Obviously, there's going to be boutique high-end techniques that I think are naturally going to stay at the medical centers. But as far as vanilla TDCS, it can be done at home, and there's many strong incentives to do it at home. The patients don't want to go in. A patient with MS does not want to take the subway, especially not now. 1 hour each way to NYU for a 20-minute treatment every single day. That is a huge burden to them, right? There's a famous with fibromyalgia, doesn't want to drive around, the Johns Hopkins looking for like parking for 30 minutes so they can go in for a 20-minute. So there's a strong, and then by the way, but also the researchers and clinicians, it's a hassle for them to have to book everyone in. So having people at home, having devices that are pre-programmed to give a certain therapy only at a certain time and even do certain assessments for you. Researchers and clinicians love that as well. It allows massive scale up. So the effort that would take you to run a 10-person trial now, you can run a 200-person trial because things are so automated. So there's just many upsides as I see it. As long as you can do things reproducibly at home, because if you send stuff home and it's some sort of rubber band, half-baked thing, then you're going to get, basically irreproducible results. So it's all contingent on being able to take the rigor of the medical center and I think it's a big thing with telemedicine, right? How do you can go home, but how do you go home with rigor? How do you deliver cognitive behavioral therapy and rehabilitation therapy and do depression assessments at home without losing stuff? That's wonderful work for biomedical engineers.
Thank you so much, Marom. I think now we'll try to let people off before 3:20. It was really an amazing talk, and everyone, I guess, feel free to bombard him with questions by email. I'm looking forward to talking to you soon. Thanks, everyone, for coming.
Thank you for your attention, everyone.
Marom, thanks so much.
Pleasure.